All right, now we'll talk about simple chemical bonding, and let's first talk about Lewis structures. So you could be asked something like this: draw the Lewis structure for NO2 plus. So that's a central nitrogen atom, and we need to figure out how many valence electrons it has. So nitrogen has 5 valence electrons. Each oxygen has 6, so 2 times 6. And then we need to figure out what to do with the charge. The charge, a positive charge, removes an electron from the total. So 12 plus 5 is 17. With the charge removing 1 gives us 16 valence electrons. Okay, now you always want to go in and tether the molecule together. And I put first a single bond to each oxygen. And those two bonds used up 4 of the electrons, leaving me with 12. I take the 12 that I have, 2, 4, 6, 8, 10, 12. I assign those. Okay, now I have 6 lone pairs for 12 electrons plus 4 that are in the single bonds. 4 plus 12 gives me 16 total electrons. So I've assigned all the electrons. Now we have to see how happy the molecule is with the assignment. So the oxygen has 2, 4, 6, 8. The bond counts as 2. 2, 4, 6, 8 for oxygen. 2, 4, 6, 8 for the other oxygen. But the nitrogen only has 2, 4. So we need to get it up to 8 also. And this is the simplest way to do that. Is for each of the oxygens to take one of their lone pairs, say this end one, erase it and make a double bond. Erase this and make a double bond. And so now all of the atoms are satisfied. The leftmost oxygen has 2, 4, 6, 8. The right one has 2, 4, 6, 8. And now nitrogen has 2, 4, 6, 8 electrons. So the final structure has 8 electrons in 4 bonds, plus 8 electrons in 4 lone pairs, which of course still is 16 electrons. We've assigned all the electrons at the end. All right, well, what about something like this? What's the Lewis structure of C2F4? We want to come up with the total number of valence electrons, so 2 times 4 for each carbon, plus 4 times 7 for each of the fluorines gives me 36 total. This structure has 2 central atoms. It has 2 central carbon atoms. I tether those guys together, and then to each of those carbons I attach 2 fluorines. And so in doing so, I've made 5 bonds, and that's used 10 of the 36 electrons. So I'm left with 26 electrons left over. I take now and follow that same process where I go to the outer atoms, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I assign those as lone pairs to the outer atoms, and that used 24 of the electrons up. So now 10 plus 24 gives me 34, so I still have 2 electrons to assign. If we had just a simple central atom, we would go and drop those electrons on the central atom. If I did that, if I, for example, dropped the 2 electrons here on the left carbon, well, it would be happy, but the right carbon would be unhappy, and so on. So what I do is instead take those 2 extra electrons and I form a second bond between the 2 carbons. Well, now that gets me up to 12 electrons in 6 bonds, 1, 2, 3, 4, 5, 6 bonds. So 12 electrons in 6 bonds, and then 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. There we go. 24 electrons in the lone pairs. And as it has to, once we've assigned all the electrons, it has to add up to the total number of electrons. So we have a weird one here now, xenon. The xenon atom has 8 valence electrons, plus 2 times 7 for the 2 fluorines. That gets us up to a total of 22 valence electrons. We take and put the xenon in the middle, and we use 4 electrons to tie the fluorines to it. We go now and assign 2, 4, 6, 8, 10, 12 of the electrons to the outer atoms. Right now I'm at 4 plus 12, 16. Okay, that leaves me with 6 unassigned electrons. And what we do is we drop all of those onto the central atom, those extra ones, 2, 4, 6. Xenon's a heavy atom, so it's okay with that. And that's all of our 22 electrons. 4 from 2 bonds, 12 from lone pairs on fluorine, 6 from lone pairs on xenon. Gets us up to a total of 22 total electrons. All right, let's talk a little bit about trends in ion size. And these two statements up here are always true. A cation is always smaller than the atom from which it was formed. So like with lithium, we take it, we remove an electron because the electron that comes away is always the outermost electron, so it always shrinks. And an anion is always larger than the atom from which it's formed. So fluoride is quite a bit larger than fluorine. Also always true, and that makes sense. We've taken the outermost electron from fluoride when we've when we made fluorine, and we've taken the outermost electron from lithium to make the lithium cation here. Also, you should know about these isoelectronic ions. All 5 of these have exactly 10 valence electrons, and anytime we have a isoelectronic set of ions like this, the one with the highest negative charge is the largest, and the one with the highest positive charge is the smallest. All right, let's look at assigning formal charges to a molecule and to a molecular ion. So first we have ozone up here, and we've drawn one of its resonance structures. And then we've taken and drawn boxes around each of the atoms. And remember, for doing formal charge, when the box cuts the bond gets split and goes half to each atom. And so this leftmost oxygen has 1, 2, 3, 4, 5, 6. Okay, it has 6 electrons in this Lewis structure. 1, 2, 3, 4, 5, 6. This one here in the middle has 1, 2, 3. So it has half of 3 bonds, or 3, 4, 5. So in the Lewis structure, it has 5. And then this one here on the right side has 1, 2, 3, 4, 5, 6, and then half the bond, 7. It has 7 in the Lewis structure. All of them, since they're all oxygen atoms, the valence for the isolated atom comes from the periodic table. They all have 6. And so let's see what happens. It has 6 in the isolated atom. It has 6 in the Lewis structure, so no charge. It has 6 in the isolated atom. It only has 5 in the Lewis structure, so it has a positive formal charge in the Lewis structure. It has 6 in the isolated atom. It has 7 in this Lewis structure, so it has a negative charge in the Lewis structure. And finally, this must also happen, always. 0 plus 1 minus 1 is 0. And this molecule, you'll see it has no charge indicated. And so when we sum up the formal charges, that has to happen. These have to sum to 0 since this is a molecule with no formal charge overall. And then for ions, what's going to happen, the sum of the formal charges must equal the charge of the ion. And let's see how we get to that. So in this Lewis structure, this leftmost oxygen has 1, 2, 3, 4, 5, 6. The rightmost oxygen has 1, 2, 3, 4, 5, 6, 7. And the nitrogen here has 1, 2, 3, 4, 5. Well, from the periodic table, oxygen should have 6. Nitrogen should have 5. And so let's do the math. 6 minus 6, so there's no charge on the leftmost oxygen. On the rightmost oxygen, 6 minus 7 has a minus 1 charge. And then the nitrogen here, 5 minus 5 is 0. So the formal charge is now 0 plus 0 minus 1 gives us overall formal charge of minus 1. And so, as promised, it sums to the charge of the ion. Let's talk about resonance structure. So there's no good reason to draw one of these structures versus the other one. And by that I mean there's no good reason that one can come up with to put the double bond on the right or to put the double bond on the left. And it ends up that in reality, the best representation of this molecule is a blend of these two structures. It ends up having something that looks more like a 1.5, a 1.5 bond, rather than a bond order of 1 or bond order of 2. And so these are two resonance structures for this molecule. The two resonance structures together are a better representation of the molecule than either one of the Lewis structures alone. Let's also talk about polarity. So although we represent covalent bonding as an equal sharing, so while we've been pretending that this bond contains 2 electrons and they're equally shared between the two, in fact, often they're unequally shared. And actually, iodine for Hi is hungrier for electrons than hydrogen is. And so these 2 electrons spend more time on iodine than they do on the hydrogen. And so the hydrogen develops a small positive charge and the iodine develops a small negative charge. To figure this out, we can look at these are electronegativity values. And the highest electronegativity on the entire periodic table is fluorine. Fluorine has a value of 4. And then everything else follows more or less a pretty smooth trend, except for hydrogen. Hydrogen, for the purposes of electronegativity, is somewhere between boron and carbon in its value. Okay, with that in mind, we can look, and when we have a choice between different inequivalent resonance structures, we can pick which one on its own is a better representation of a molecule. And so, for example, this is the way we normally represent CO2, a carbon double bonded to an oxygen, double bonded to another oxygen. However, in terms of the octet rule, this is also a perfectly good structure to have a triple bond to one oxygen and just a single bond to the other. And let's see why this structure actually ends up being better. It's better, according to this electroneutrality rule, because if there's any way that we can manage it, we try not to have charges on the atoms. This has no charge on any of the atoms, whereas this one is having a positive charge on one oxygen and a negative charge on the other one. Let's look at something slightly more complicated, OCN, the cyanate anion. So there's 3 different structures, kind of same deal here, where we can have a single bond and a triple bond, 2 double bonds, or a triple bond and a single bond between the atoms. Because of how the electrons get assigned, though, structure A here puts a negative charge on the oxygen, structure B puts a negative charge on the nitrogen, and structure C puts a positive charge on the oxygen and a 2- charge on the nitrogen. Well, by this electron neutrality principle, this is the worst structure, this last one, because we have bigger charges. We want to avoid charges at all if possible, and if we must have charges, then we want them to be as small as possible. So C is the worst, and then we have to decide what's better, A or B. And if we go back to our electronegativity table, OCN, so the atoms that are in there are O, C, and N. So oxygen has quite a bit higher electronegativity than nitrogen, and so oxygen is the better choice to have the negative charge than nitrogen. So this structure is the best. This would be the middle structure, and then this is the worst structure. Okay, A is the best, B a little bit worse than A, and then C much worse than A. All right, finally, let's talk about taking bond dissociation energies and estimating enthalpies of reaction. So we have this reaction, H2 plus Cl2, to give us 2 HCl, and we say we want to estimate the energy of the reaction. Well, we can think about this as taking H2, now we've put it more like a Lewis structure, and Cl2, breaking these apart. Okay, think about these like Lego pieces. We break this Lego set, and then we make these new ones. It costs us energy to break this bond. It costs energy to break this bond, and it releases energy when we make the bonds of the products. Okay, breaking bonds and reactants always costs energy. Making bonds and products always gives energy. It's just this enthalpy is determined by the balance between these two, because it's not exactly the same amount. This cost, this gives, but the cost benefit tells us how it works out. So let's look at some actual data. So it requires 436.4 kilojoules to break the HH bond. It requires 242.7 kilojoules to break the CL-Cl bond. Okay, so there's the total energy that we have to put in. This is the cost and the cost benefit. We get out 431.9, and these are identical, so 431.9 for both. So it costs 679.1. The benefit is 863.8. When we do these, this is weird compared to some other things. We do reactants minus products. Okay, so reactants minus products, this gives us a negative enthalpy. So this is a exothermic process. We get a release of energy. The bonds in the products are stronger than the bonds in the reactants. Okay, let's go through the whole thing with a little bit more complicated example, which is like something you might see. Complete and balance the reaction if needed. Okay, so we have N2 reacting with 3H2 to give us 2NH3. And this is a very critical step, this next one. Rewrite everything with Lewis structures. Okay, so Lewis structure, Lewis structure, Lewis structure. The reason this is critical is we're going to need to know the type of each bond. And when you're given a table of values, you're going to need to know whether this is an N triple bond N, an N double bond N, or N single bond N, for example. So let's take this now and reduce it to what we have here at the bottom. So we have 1 mole of N triple bond N, we have 3 moles of HH bonds, and we have 6 moles of NH bonds. 1, 2, 3 NH bonds times 2. 3 times 2 is how I get the 6 NH bonds. Okay, then we go to a table and make sure we pull out the right data. So this is the N triple bond N, 941.4. For H single bond H, 436.4. We have 3 of those. And I'm going to sum this up now. And this gives me a value of 2250.6 kilojoules. And then on the product side, find my NH bond, H bond N, okay, right here, 393. And there's 6 of those, so 6 NH bonds. I do the math here, I get 2358. Okay, now finally, to estimate this enthalpy of reaction, I take the reactants minus the products, and so this process is again exothermic. We get a negative delta H value out.